Hello, everyone. Welcome to today's stream.
Welcome.
We have such a cool group of people. We've listened to you guys in the community. You've really wanted to learn about deformable bodies and cloth simulation. So Edmar worked really, really hard and compiled the top guys to talk to you about this today. So without further ado, I'm Wendy, and of course my co-host up here, Edmar. Edmar,
Hey,
take it
Wendy.
away.
Thank you so much. And Wendy is not joking. This is the dream team of digital humans and physics and soft body and cloth. So we are going to be able to take all your questions during the stream. We're gonna show you a couple cool things, talk about what's on the roadmap, what you can do right now. So we're gonna go over quite a bit. It's just me a full packed hour. We would love to be able to answer as many questions as possible that you have, since it's been a highly requested live stream. So please start posting your questions in the chat, and we'll do our best to answer them. If we can't answer any of them during the stream, we'll hit afterwards, or we might jump onto the community voice chat channel following the stream. And really quick, just as a quick announcement, we do have the Omniverse Machinima contest going on right now. So if you have not heard about that, that is a really cool contest where you can make a small trailer using some assets of ours or your own. We've got some assets from game publishers that have been contributed for this. And you can jump on the contest page to read all about that. You have until end of June to do your submission, so there's plenty of time. And we have a channel on Discord specifically for that called Contest Machinima, so you can post your questions there related to the contest. So we're going to have a stream in a few weeks with Benny D, I believe, to talk about workflow and how he goes about making an animation using Machinima. So that should be a lot of fun. Yeah, we also have an upcoming live stream with Twitch and with I'm sorry, not with Twitch, with TurboSquid and with Adobe. So we're starting to post these on Discord. So if you go to our Discord, which is discord.gg/NVIDIA Omniverse, there's an events item on the top left of the navigation bar, and you can see the upcoming live streams there and opt in for notifications. But let's get started because this is going to be really fun. And let me introduce Simon. Simon, thank you for coming on. It's so awesome to have you on the stream. Do you want to give a quick intro to who you are and what you do at NVIDIA?
Oh, you're muted, Simon.
There you go.
That shows you how veteran or non-experienced I am with this stuff. But thanks for having me. I'm Simon, and I lead digital human efforts at NVIDIA. What that means, I'll talk more in a second. But one cool thing is I get to work with all the smart people that are on this call. Many of you may or may not have seen some of the work from NVIDIA regarding our contributions to digital human. A lot of our focus today is on animation performance, things like audio to phase, and our upcoming features like audio to gesture, where you can use just your voice to drive body motion. And a lot of emphasis on the rendering side, how to render realistic characters really easily from the Omniverse ray tracing, path tracing, etc. With that, a lot of people have been curious about how about clothing, how about soft bodies? What solutions are we offering? Anything? And the answer is yes. There has been, physics is a really huge part of NVIDIA, just like AI is. And so there actually is solutions out there today released with Create. And the team here, the physics team here, is the wizards behind those technologies. So we brought them on here to talk more about it. So without further ado, I'll hand it over to Michelle.
Thanks, Simon. I'm really astonished by the wizard in here. So I'm regarding myself as a normal engineer, but thanks. Yes, hi, I'm Michelle. So I'm the developer manager in the Physics SDK team. So as Simon mentioned, we have some few features already released with Omniverse Create, which will be beneficial for the digital human project, such as the deformable body simulation and particle-based cloth. So I'm not sure you guys are familiar with what is FEM-based soft body simulation, right? So I'm going to just give a brief description about what is the tech behind it and what kind of technology we're using to simulate it in real time, right? So FEM based deformable body, it's basically the model have we break up the model with a list of small elements. So that is a finite element method, right? In our implementation, we're using a tetrahedral base, and the solver we're using is based on correlation and also Leo-Hawkian as well. So we combine both model together and then create a new form of solver. And we solve for both stretch and volume conservation. And we use a really well-defined material property, just like the Young's modular and portion ratio. So to let the user to define their own property as close as to reality as possible, and then we're using those terms to measure the deformation gradient, and then in order to simulate the deformation in there. And this approach is also using the XPPD style unconditional stable approach. So if you get your hand into the Create and you create a soft body, please abuse it. And if it doesn't work, please come to Discord and tell us. We will try to improve it. And of course, beside the deformable body simulation, one thing really beneficial for the digital human project, of course, is cross coding. Is everything is important, right? So the current approach we release is based on particles. So it's again it's an XPPD style spring derivation solver. The way we simulate clocks is using we create a list of particle, and we're using a spring to connect different particles to simulate the stretch, shear, and bending property of the clocks. Of course, the spring is defined by a standard Leo-Hawkian, Steve, and Dampington, and we also support aerodynamic as well. So you can have a really simple wind and then lift and drag effect in there. So Simon will show you all those cool tech later. But at the moment now, right, I'm going to pass to Philip to show us how did we do simple authoring for the deformable body in Omniverse.
Right. Hi, I'm Philip. I just shared my screen. I hope it's visible, Wendy.
It is.
You should be seeing great, yeah. I'm an engineer on Michelle's team and working on physics in Omniverse. And yeah, I'll show you a bit how you can author deformable bodies in Create. And what I'm using here is just the latest Create beta that we released. My brief session will have 3 parts. So first, I just show you how to create a deformable body and a couple simulation parameters that you should be aware of. Then I'll show you how you can rig up a deformable body using a physics mechanism to drive it. And finally, I'll show you a demo that we created that puts these 2 concepts together, where we simulate a deformable human hand that interacts with physics objects in a scene. Right, so what we'll be doing is turn this mesh into a deformable body. But before I'll do that part, I'll just very briefly touch on physics in Omniverse Create. What I did beforehand is rig up this mesh here as a rigid body. This will also help to very clearly see the difference between a rigid and a deformable body as I show this. I already did it, but I'll just show you how you could rig up this asset as a rigid body, and that is just by adding physics. It's already grayed out because I added it, this rigid body and colliders preset component. And if you do that, all you need to do then is to hit play, and the simulation will run. After every simulation step, we update the transforms of the meshes, and you see the output. And if you shift left click, you can also grab them and throw the body around. And as I mentioned, this is a rigid body, so as it hits this ground plane that I have here, it will not deform, in contrast to the deformable body that we're going to create next. So, right, so I said we'll turn this mesh into a deformable body. It's quite easy to do. You need to work on the mesh itself, and just as before, for the rigid body, you go to add physics, and instead of rigid body, you go to deformable body and add that component. And that's it. Quite easy. So we'll run the simulation again. And now you see you have this squishy bust.
That is so much fun.
So
Oh, yeah.
let's take a step back just a second, because some people
Yeah.
might be joining us. So what would be the reason why people would want to use deformable bodies, and what type of people would really be most interested in doing this kind of stuff?
I guess I'll touch on this a bit when I show the demo at the end. That yeah, if you simulate a human hand using this deformed body, then you will get a physical interaction with another object, for example, the rigid bust, right? And then you would see the body deform based on the physical interaction. And I mean, Simon will know this much better. Simon Ewan will know this much better. The traditional approach of animation, where you have, I guess, an animation skeleton, and then you drive a mesh using that, where you won't have this interaction directly, unless you do more, I guess. Would you say that could be a motivation, Simon?
Absolutely. I mean, in real life, there's, our flesh is soft and they kind of jiggle and they move around. And if we just did the jiggling, doesn't collide, that also doesn't seem real.
Yeah, right.
Really,
Yeah.
deformable bodies for anything that isn't rigid, as in like a marble statue, that needs to have some compression, holds the volume, has some collusion. It's really for a wide range of that. In particular, for characters, it could be a creature, it could be an animal, it could be a digital human that you want to give some life to as they move.
Mhm.
And I think what the team has done here is be able to provide this real time. In the past, in visual effects, this stuff is very expensive to calculate, so very slow. It's not real time. So you got to wait for what just happened with the statue. You might have to wait a few minutes at least. So we're doing this in real time, taking advantage of our GPUs.
Very cool. And on that note, actually, we have a question from John. He's asking if you can show the wireframe and what is the poly count on this deformable body mesh.
I'll get to that in just a little bit. So yeah, John, just hold on a few moments. Yeah, right. So as a next part, I would talk about some of the simulation parameters that you can tune to change the behavior of the deformable body, and I'll get to the tap mesh and the resolution as well. Right. So just as with render materials, what you can do is you can create physics materials that have physical material properties, and you can add these to a deformable body. So I'll create a physics material, and now we could choose like a rigid body material, or in this case, we'll choose the deformable body material that will add to the deformable body. I can do this by going to the mesh that I turned into a deformable body and scrolling down to the deformable body widget. And underneath you'll have this physics materials, where I can select the physics material. And now the deformable body simulation will use the material parameters that we set here in this material. If I hit play again now, it looks exactly the same as before, because if you don't assign a material, we use a default material, which is the same as if you just freshly create the material. But what we can do, for example, Michelle already touched on this, the Young's modulus is one of the material properties that describes the stiffness of the material. And I can reduce this parameter to make it less stiff and more squishy. I'll go quite extreme so we see it quite clearly. Divide by 1,000 and run the simulation again, and now you see how it got a bit more squishy. Just to get a yeah, maybe to make this even clearer, I'll do a side by side where I'll just unassign a material again from this duplicate. So use the stiffer default material. Run it again, and now it should be very clear, yeah, that one is much softer than the other. And that's just one of these material properties. You can tune other properties in the material too, such as a friction, for example, and how it, yeah, basically changing the sliding behavior of the deformable body. Right, and now for this parameter that John asked about, the resolution of this, Michelle talked about this, that we basically subdivide the mesh into little tets, little cube, in a way cubes. And we can visualize that actually using debug visualization. So you can go to this eye in the viewport and then go to the physics, debug visualization options, deformable body, and hit selected, and then you'll see either the simulation or the collision mesh. And the simulation mesh is what Michelle mentioned, this subdivision that the solver, that the physics engine runs on to compute the deformation, for example. Then you can also visualize the collision mesh. And to answer your question, I don't know what well, along the longest axis, the resolution here is 10. So this should be 10 cubes along this axis. The other mesh that we can visualize is the collision mesh. Both of these meshes are auto-computed. You don't need to do anything for that. And the collision mesh is just used to generate contacts with other physics objects in the scene. And then these contacts are then resolved by the simulation mesh and the solver. Right.
One thing I want to point out, sorry,
Yes.
Philip, one thing I want to point out in here, right? Those, the resolution is based on the default value, but the user have a complete control about the resolution, right? Yeah.
Let me show that. Yeah, like, yeah, exactly. So it could be that maybe this resolution is not high enough to capture all the details of the input mesh. And then, as Michelle said, you can go to the deformable body properties, and then you find the simulation mesh resolution. So here I can increase it by a factor of 2, and then you see you get a much higher resolution, then can capture more detail of the input mesh, which I guess you could use which would be useful if you want little features to deform relative to the rest of the body, which is detail that you could lose with a coarser resolution. Now, let me turn off the debug visualization.
I think
yeah.
Just to add, I mean, it might seemingly, it looks like low res cubes, but in practice, a lot of times it's enough because unless you're doing like little pinches onto a really tiny area, most of our our muscles move. They're kind of masses that they move and they collide with. So this is actually more than enough. If anybody's curious.
Yeah, in case you did, so, right. So I'll just run the simulation again, because this is one of the pitfalls you can fall into. So now I just increase this, the resolution of this one by a factor of 2 over this one. This one also has the softer material. Keep that in mind as well. So this one should be stiffer. And now if I run the simulation, you'll see that they're almost the same squishiness, or very similar squishiness. And the reason for that is that the solver that doesn't converge in the amount of iterations that I gave it in the parameters. And what you need to do in that case is you can increase the number of iterations that the solver can run on. And you find that property in the advanced rollout. You have the solver position iterations. And what I can do here is just double it and run the simulation again. So the solver should converge better now. And you see how we recovered some of the stiffness from the lower res version. Now the trade-off here is, of course, if I run more iterations, this is computationally more expensive. So I'm not sure if you paid attention, but my FPS will have dropped for the higher iteration simulation. So that's something to keep in mind of, like this trade-off between the resolution of the sim mesh the number of iterations you should run to get the desired behavior and the FPS or performance that you require. Good. Let's switch gears to the second part. Unless you have, unless somebody wants to comment or.
I think I think everyone's enjoying what they're seeing very much. So I think for some reason the resolution we're streaming at is lower than typical. Wendy's looking
Really?
into it.
Yeah, it's on Twitch. YouTube is, I'm streaming at 4K on YouTube, but on Twitch it's only going to 720. I'm trying to play with that. Sorry about that, guys.
So to compensate
I
for
think-
that, if any of the presenters just remember to kind of give an audio cue to what you're clicking on, in case they can't read the menu.
Ah, I see.
But
Right.
thank you.
I hope I was explaining it more or less
Yeah, I think
clear
so.
enough. Yeah. Yeah. So
Yeah,
every time I hit, like, so say simulate, I basically hit the play button here.
Mhm.
Yeah, I'm aware like the context menus were probably a bit small. Sorry about that.
I think it's maybe
Yeah.
worth talking about one particular thing as well that's not mentioned, which was there's a tick box there called Enable Self-Collision. So with these particular models, we're not seeing any self-intersection, so it's reasonable to have that disabled. But this is actually quite an important tick box to turn on if you've got something like, say, you decide you want to simulate not something that's kind of a single kind of object that won't really have self-intersection, but like if you created like a weird kind of octopus creature that had tentacles flapping around, you'd want to have that
Right.
turned on to be able to get the self-intersection. And it's also worth pointing out that the simulation that Philip's got here as well, that the two soft bodies can collide against each other and they can collide against that rigid body as well, so they can all interact with each other.
Yeah, that's the thing I want to address as well. So basically, everything in VSET, right, is a two-way interactive. So you see, soft body is collide with soft body, and soft body can collide with rigid body as well. So for the self-collision case, right, so if you turn on self-collision, it's expensive, of course. But let's say Philip will show you a demo later on. Is the whole hand. We're using FEM to simulate the whole hand. But if you have a finger like that, right, you need to turn on self-collision. So those things won't go past to each other. So you can use that. And what else feature? Also yes. I think Philip didn't prepare this, but again, I think I really need to cannot stress enough about the two-way coupling. So soft body can interact with soft body can interact with rigid body, and also can interact with the particle cloth and particle system, and lots of all the feature inside VSET as well. Sorry, Philip, please go on.
No worries at all. Thank you for these additions. Yeah.
You know, one question actually, if I can interrupt really quick, because this is something I think only people in this room could answer. Hi there. The sim mesh looks based on lattice voxelization. Is there a possibility to get an option API for using other element types, especially hexes?
Yeah.
Well,
We all you go on.
Yeah, so we have the ability to simulate tetrahedra or hexahedra as a simulation mesh. The tetrahedral mesh that we're generating here was actually a hexahedral mesh. We're displaying it as a tetrahedral mesh, but it's simulated behind the scenes as a hexahedral mesh. But that's optional, that you can do one of the two. And it is also possible to use the collision mesh as the simulation mesh as well, so we can also do that. That just introduces a number of challenges to solver convergence. Mainly because what we get with this kind of hexahedral mesh that we've shown here is we get this really nice regular structure, which makes it really well suited for things like parallel solving on a GPU, and you've got really even mass distribution between all of the vertices and all of the elements, which makes it ideally suited to simulate. But if Philip now loads up the collision mesh as an alternative, and we can see this, this might be quite well formed, and this might be a terrible example of it, but you can probably see that there will be some places where there will be some irregularities in it, which doesn't look present in this one.
Looks
looks
quite
like a very
nice.
well
No,
modeled- This looks like a brilliantly modeled mesh. So
no, you still can see it. You can see it definitely on the, some of the lower part. So that that one. Yeah. No. Yeah, that is smaller, right?
This one.
No, on top go further. So that one will be smaller, and then on top will be bigger. You already show it. So basically, if you simulate the tetrahedron, the simulation mesh and collision mesh is exactly the same form. So yes, as Kia mentioned, right, will influence the solver converge because the solar will be easy to show uniform mass distribution. So it's a user's choice, right? Of course, we provide all the functionality for you. If you think you are matching the simulation mesh and condition mesh is beneficial for your simulation, you are absolutely welcome to do so. So it's no limitation at all.
We actually got a question, which I'm sure this is one of the first things your team tested when you came up with this amazing technology. Would there be a way to simulate a cake splat on the ground? I'm guessing yes. But have you guys ever tried that?
Is there
Yes,
is
but
there
we
cake?
wouldn't. Yes, but we wouldn't be doing this with an FEM because when it hits, we want it to fracture and break apart. So we do have particle-based solutions for this. So we have in the works the material point method, which would be ideally suited to do this. I mean, that's basically pretty much exactly what that's ideally suited for. That's a lot more expensive than
No cake.
FEM. So it's still work in progress. We also have the ability with our XPBD particles to do something that will approximate that as well. It's not as well defined in terms of the kind of material properties and the simulation behind it. But as an effect to be able to achieve it, I think it could do that we could shape match with a weak constraint that would hold the cake together, and on impact it would just splat and turn into bits. That would definitely work.
Yeah, it's exactly what Kia say, right? For visual effect, you can use the XPPD approach. So the one we're talking about using to simulate the particle clocks, it's exactly the same thing, right? It's a particle system, different property and simulate different thing. But if you want a physically more accurate, right, a fracture and whatever, right? In there, we have something work in progress. It's MPM, material point method, right? It's the same theory behind FEM, right? We also solving the particle based on energy network, but however, compared with the FEM, because this FEM, if you change it, you need to change the topology, so it's expensive to do. But MPM, because it's a particle base, right? So that is naturally let you to break the bond of it without any penalty on it. That's why we prefer to using the MPM method to simulate something like that.
Very cool. And this might be related. Are you able to localize stiffness with a texture map?
Yes, we definitely are. So you're able to apply per tetrahedra material properties. So this is something that's not fully supported yet in Omniverse, but it's something that'll be coming in the next version. But the actual underlying simulation has the capacity to do this. And we could probably do this via some kind of scripting mechanism already, I would imagine, but to do it through the visual side and painting it. That's
the idea was this is USD concept of subsets of a mesh, and then you would assign a material to the subset. And here we just target the tetrahedra instead of triangles, I guess.
Okay, cool. And Happy Horse is asking, can we simulate just part of the mesh with some kind of weight map painting?
Again, it's one of these things that is conceptually possible, but I think there's tool side work required to make it easier.
Yeah, we don't have.
I think via scripts and things like that, it's probably something that could be done fairly rapidly, because you could gain control over a subset of the vertices and move them around while the other ones are simulated. But again, I think there's some stage to go further to make this be something that's a very smooth and user-friendly experience.
Can I ask what is the use case for that? I mean, because if it depends on if it's important, right? And we see the use for it, of course, we would love to support that on the tool side. So is that Happy Horse?
So
Yes.
Happy Horse, that is a request directly from Michelle. Let us know what you're thinking about, and we'll see if we can.
Yeah, I mean, there are other options where we could have like half of the mesh as a rigid body, if you can subdivide it, and half of it as a soft
and then
body.
use what I'm about to show. Yeah,
attach it with the magic that Philip's about to show as well, which would do it as well.
So let me continue, because Simon also has a part has the cloth.
Well, we're going to run out of time. Let's go.
It's exciting, and we need to get going.
Philip,
Anyway,
can I add one thing? I think it's really important. You're running on a laptop, right? On a 3080, because
Yeah,
people
it's a
might not be able to
3080
see that.
gaming laptop. Yeah.
So that's actually, I think, pretty important for people to know how optimized this is. Not that many years ago, like my years in visual effects, this would take a
Can
workstation
I do
maybe
this?
a minute or two
That's my laptop.
to
Wow.
compute each frame. So I don't want to understate the importance here of that you can do FEM solves in real time, this kind of complexity. So it's pretty awesome.
Very cool. And just before we lose this train of thought, Happy Horse did reply back. This is his question was regarding the belly of a character,
The more
which I,
yeah,
data,
I
so
guess is pretty
so
interesting.
yeah, I think that would definitely
Okay.
be a situation where you would have part of it that would be completely animated, and then we could use the same techniques that Philip's talking about now to attach onto it. So
Yeah, basically make the belly part a separate mesh and deformable, and then attach it to the animated mesh. Yeah. Yeah. So let me show attachments so we can give Simon enough time as well, because I'm sure there will be some questions there too. Right. So the next part is, I said, how to drive a deformable body using a physics mechanism. And here I have this example. So this gummy bear is a deformable body, and we're going to make it do sit-ups. Yeah, I just have a little Python script to animate it, and it just goes 1, 2. Yeah, yeah. Right.
That's
And the way this
awesome.
works, and the way this works, so
He's so
inside
cute.
the deformable body, we have this very simple mechanism, just 2 rigid bodies that I can make to move, and then the gummy bear is attached to it using attachments that we have, and then it does it. So let's do this part. I prepared an unauthored stage as well. So now it's the same. What I already prepared is the mechanism and the deformable body. Let's show the mechanism again. And our goal is to attach these 2 bodies of the mechanism to the deformable body gummy bear. The way you can do this is you select the gummy bear mesh. Let me just turn off the debug viz quick. You select the gummy bear mesh, and then also the part of the mechanism that you would like to attach to. You go to create, physics, attachment. Now we just repeat this process for the second component of the mechanism. Create, physics, attachment. So yeah, for the ones with the low resolution, I basically right-clicked on one of the selected prims in the stage window, and then in the context menu, I went to create physics attachment. So let's show the gummy bear again, and start the simulation, and then my little animation. So now it's attached. You might notice that it's a bit more wobbly, and that is because by default we just attach the intersecting vertices of the deformable body with the mechanism parts. But you can make this attachment more firm by adding additional attachment points. And you can do this by selecting the attachments. So I selected the 2 attachments, and then go down into the property window to their properties, and then I can click on attach rigid surface. And what happens then is that we basically sample along the surface of the mechanism parts that overlap with the deformable body, and these sampled points then create additional attachments. We can also visualize that using the debug visualization. So I can go to attachments, selected, and now we see these sample points here along the mechanism parts, and that provides a better connection. Right, so now let's simulate again. And we'll have this firmer attachment now. So now it's back to this firmer behavior. Good. Right, that was attachments. So let me get to the last part, just this demo where we put this all together. If you go to Window and then Simulation and click Demo Scenes, then our demo scene window pops up, and you can go to Demos, and then there's this hand pouring liquid demo, where I click Load Scene, and it will open. And what we'll have here is this human hand is a deformable body. So basically the same as the gummy bear before. And inside there's a mechanism that will drive it. So let me just play it. And the hand will interact with this glass here, which is a rigid body that's filled with particle fluid. So again, highlighting this the interaction that's possible between all these physics objects, and we'll just pour it. So let me just show you what's going on in terms of mechanism. So I hit the deformable body and now just show the skeleton bones inside, and that's again this mechanism analogous to the gummy bear example. And I drive this mechanism using mocap data that I got from using a leap sensor. Well,
Did Philip
dropped,
gone?
Uh-oh.
am I back?
Oh, there he's back.
You're
He's
back.
back.
Okay.
Flickering, but back.
What happened? Yeah, this doesn't look good. Let's close and hand over to. Yeah.
But, I don't understand why it's
alright.
crashed, but that demo is already released, right? So your guy
Yeah,
can
so
actually
you can try
get
it.
your hand on it. You try it.
We
to
have
us,
problems
it's a
with
pretty-
screen cap software too,
Yeah.
where the GPU
Before it's a
crashes. So I assume it's a
quite
similar
stable.
issue
I
with
don't know
sharing
why.
This is all real. This is all real time.
Yeah, live.
Yeah,
It's
lie and
live.
retire and crash.
And that's the end of my demo. Yeah.
Thanks.
With-
All right,
Okay,
guys.
Now let Simon, please. Otherwise
Yes.
we run out of time. Yeah.
Yeah, I'll rush through it. No, but thanks, Philip. And yeah, my name is Simon too, as you learned already. Thanks for Simon One's team to provide these meshes that I used for this demo. Okay, let's get started. So we're gonna just turn this t-shirt mesh into actual particle cloth. So we do this by adding a particle cloth component, add physics particle cloth. Okay, as you can see, like it did add a particle cloth component to the mesh here. And it also created a separate object that is a bit different than the deformable bodies that Philip showed. So there's a particle system that actually owns the particles that are being simulated. And the reason for this is that there can be a ton of different objects that can feed into the same particle system, and they can all interact with each other in a very efficient way. Let me show you how far we got so far. So that's not very convincing. So the next thing is to add actually collider components to the character model here. So I'm just going to select all of the ones that I care about, right click, add physics collider preset. Okay, let's see what that does. Okay, it stays in place, but well, looks a bit puffy and a bit erratic down here. So what's that? So we need to tune the particle radii that are used for collision detection. Let's have a look how to do that. Those are parameters of the particle system under advanced mainly. However, like we should really turn on debug visualization, because that's a great help of knowing what we're actually doing. So I go here. So Philip showed deformable body attachments. I show particles. So cloth particles, cloth mesh is already enabled. I'll turn this on. So you can see this is now it makes sense that this puffs up like this. So this is not good. We got to change this. What is also very useful for debug visualization and tweaking radii and particle systems is this physics simulation debug window. So I like to drag that down here because then I can at the same time tweak the properties over here. So here, this is the particle debug visualization submenu, and you can see I can change here the radii I want to visualize. Now there's the particle contact offset is sort of like the master switch for this, and I go to the particle system. So this is set to 5 here. I will just like turn this down a little bit, but we will refine it anyways. So this looks a bit better. This basically defines at which distance particles can interact with each other's. Yet nothing to do with how they interact with the collider though. So for the collider, actually, we're mostly interested into this rest offset because that defines exactly the radius at which they collide with the collider. So let me tweak that. Maybe one word to these auto-computed values. So I mentioned this is kind of like the master switch. So this defines the maximum radius particles can interact with other particles. And those auto-computed values are basically derived from that with constants. So if I want to specify them, we cannot display them right now, but we will work on that. But if you want to like specify them, you can just go ahead and yeah, I prepare that. I know already what a good value is, so 0.5, and you can see that the particles pretty much already rest on the collision surface. So so that's a good rest state and a good size, therefore. The contact offset, I'll make a little bit bigger. This basically, and let me visualize it too. This basically means that as long as those are overlapping with the colliders, there is a contact. And we sort of want for a resting contact situation, we want to have persistent contact. So we'll make them a little bit bigger than the rest offset so we don't get any jitter. While I'm at it, I also want to define the particle rest offset, which is in this case not very relevant, but it would be for cloth self-collision. So this will basically define at which distance particles would collide. Now you can see they're already kind of like set to a value that's already overlapping, so it would sort of, you would expect it to explode. But we have like a collision filter that is based on this rest state that you see here. So whenever a particle is initially overlapping already, like there will be no collision resolution. So what would happen if this sleeve bit here would like collide with the like main body of the t-shirt, like they would start to collide at this radius. So that's basically what's going on. And I'm just gonna well, set this to maybe 1 or so. All right, but let's turn off the debug visualization and get back to our t-shirt and see how it looks right now. I simulate, it's pretty much better. However, what I don't like is that it kind of settles on the body and it stretches a little bit too much. So we're going to tweak that. Now stretching is like, and Philip already described like a similar phenomenon with the deformables, is dependent on many different factors. One being gravity and the mass of the particles. Another being like the spring stiffnesses that are used to simulate the cloth. But then there's also like the tessellation of the original mesh will have an impact, because like that will define how many small springs are being created. And then last but definitely not least, the solver iteration count. So the solver, if the solver doesn't converge, it basically results in stretching, and similarly the time step. So let's try to improve that. Good practice is to start with the mass. So I go to add physics mass. I'll add a mass component, which lets me just define the mass as a whole on the whole t-shirt. I'll set this to 0.2, like 200 grams seem to be a good t-shirt size. Weight looks rather similar. Now let's tweak the spring stiffnesses. Here you can see it's already pretty high. If I make this higher and I go on to simulate it, it looks pretty much the same. And this phenomenon kind of like indicates, as Philip also showed previously with deformables, that the solver cannot catch up. So what we're gonna do is like we are gonna turn on. We go to the particle system, advanced, and change the solver position iteration. Tune that to be twice as much for this example, and you can see it's much stiffer, and I'm kind of happy with that now. Yeah, that's it for the t-shirt. Now, since we're quite tight on time, Michelle, you got to tell me, should I show the cape still?
Yeah, please,
Okay.
because some
Okay.
audience already asking for us, so please do.
Oh, right, yeah, correct. Thanks. Okay, I'm not gonna author it actually. I'm just gonna show it in a separate stage. So I have here like this little cape attached. It's a bit low end, but it should do the job. Now so since I'm not gonna author it, I can just tell you what I did. I basically click the mesh itself and the collider, and I go right click, create physics attachment, and then I would create an attachment, but it should already be authored here. So I'm just gonna visualize it. Okay, so here you can see I maybe for completeness, the attachment is usually added to the cloth part of the two objects, and we can tweak like the overlap offsets and filtering offsets, which defines how the attachment points are computed based on the overlap, basically. Yeah, so to make sure that it's attached. And like if I simulate that, actually, let me first open a script which adds some wind. So, okay, run this one. Let's see where that works. Yeah, seems to work. So you have your cape.
That's awesome.
That's so cool.
I have to say,
Yeah.
so the whole time you've been showing us off this example, the previous one, the t-shirt, people are throwing hearts. Wow, it's impressive. Looks perfect. Very great demonstration of the fine work you are all doing. So the community loves it.
Oh,
And
even-
I want,
Thanks.
Simon, I think I need to stress something as well, right? So just
Yes.
now, Simon and Philip both talking about the solver if it not converge, right? And then you need to increase the iteration count. Yes, that's absolutely correct. But I want to stress for the clothing, right? We're actually working on some technique to trying to make the t-shirt converge a lot faster. So the Crocs converge a lot faster. Those are scheduled on work. So we will trying to deliver the less iteration. So you don't need to tune it, but you can preserve all the structure of the t-shirt. And also Simon's example, you can see a lot of wrinkle as well, right? So under the armpit, everything you have the fold in there. So yes, but yeah. Sometimes you need to run more iteration, so we are addressing those issues. So thanks to Simon again. Thanks to Philip. That's a great presentation demonstration. So now for us, right? So we have the soft body simulation for digital human. It's the muscle and skin, all this stuff, right? We have the Crocs tab for the clothing. Now, what will come in for us? Of course, we talk about what Simon showed in there is the particle-based cloth. So one of the problem with that approach, right, is because it's spring-based. So we are now working on something more high fidelity. And also we're working on a hair system as well to go with the digital human. So we have the full set, right? So now I will let Kia take the lead and then explain to us what kind of technique is behind it. And then we are also working on that.
Hi guys. So yeah, like what Michelle said, so what we've shown here is this particle-based cloth, which is part of this unified XPVD-based particle simulation that's able to simulate shape-match shapes, inflatables, so we can do like balloons, cloth, it can do fluids, it can do granular materials, it can do ropes, it can do a wide range of things. If you're familiar with anything like Houdini's Vellum solver or even NVIDIA's Flex, which has been shown before, it's quite similar to the kind of technology that was used in those. So what we're moving on with this is introducing a more high fidelity cloth model, and this is our finite element method based cloth model. So with this case, where we've seen FEM working with tetrahedra and with hexahedra, as Philip showed, we're now going to be working on FEM that's using triangles. So basically, you'll get the same kind of properties like Young's modulus and Poisson ratio, and in addition to this, we'll have the notion of the thickness of the cloth. And from that thickness of the cloth, we'll also add in a bending constraint. So what we're solving is we're solving the energy density on these triangles, and we are basically solving for area preservation and also for stretch. So area preservation is something that we can't do straight up with springs just because of the way that it works. When the springs, they stretch, they contract, they're trying to go to a rest length. But if you took like a sheet of like rubber or something and you pulled it, you would expect it to contract around the edge to kind of preserve its area, and those kind of effects won't happen with just pure spring-based cloth. But with this technique it will, so it means that we can do things like lycra that are very accurate. But because we're using these materials like Young's modulus and Poisson ratio, it also makes it quite easy to define behavior where you're not having to tune kind of fiddly spring properties, but instead you're able to get, for example, material properties for things like, you know, cotton, wool, things like that. The bending constraints, as we mentioned, they're based on the properties of the material and the thickness, and they form an angular constraint rather than what we'd be doing with the spring-based system, where we'd be using distance springs. And this allows us to do more detailed angular effects, so we can actually simulate things that are very rigid. So we can have like kind of very heavily starched kind of like cardboard collars on a shirt, and they'll hold together really well. And then in addition to that, because it's all now triangular based, we can actually solve for contacts on triangles. So as Simon was saying, when we're doing particles and we're doing collisions based on particles, so there are fairly cases where you could have like kind of acute edges where that would pierce through between the gaps, and you have to increase the particle sampling frequency or increase the radius of the particles to try and catch those contacts that they're intersecting. That won't be necessary anymore. So it means that with this kind of simulation, you'll be able to simulate very flat, very thin, natural looking cloth that would get accurate collisions. And then, yeah, what she was saying as well, in addition to that, is the hair simulation. So the hair simulation is something else that we've got working in the background. So this is like an evolution of some of the hair tech that we've used before. And it's a hybrid solver that based on XPBD strand simulation. But what we do is we combine together the kind of some of the fidelity that have been used in the past on like VFX with also some of the approaches that have been used for real-time hair. So for real-time hair, what we've done in the past is we've done a kind of density solver basically. So in other words, you're solving not the individual strands of hair interacting with each other, but you're solving a global density function to try and keep the shape and structure of a hair. And we have support for that, but in addition we have support for full detailed strand collision. And the nice thing about this is the fact that we can scale up so that you could have a vast number of characters with hair, and we could simulate them extremely fast and extremely efficiently, and then we can transition with LODs and distances to show full detail of individual strands of hair interacting with each other, and we can do all this in real time. With this, it's also got the same kind of bending constraints that we're talking about with the cloth, which is solving for a dihedral bending constraint that can follow down to simulate curled hair and things like that. So we're not just stuck with kind of straight hair, ponytail, we can do curved hair, curled hairs all interacting with each other. And we also have the support for defining like a global style constraint as well, which will kind of hold together the hair structure and style. It's also got like damping for the bending and structural things. So we can hold together not just kind of floppy hair on head, but we can hold together really nice styles. We can have really detailed interactions. You can have parts of it ponytails, all this loose hair falling over shoulders. So it's going to be really cool, really high quality hair simulation that we can show that's going to be able to go right up to kind of movie quality stuff that you've seen. And
Yeah, hopefully we can do all this in real time as well, right? Because of real time is our team's strength. Okay, thanks, Kia. So that's my team. So I'm so proud of you guys and so proud of working in NVIDIA. It's an absolutely amazing place. Emma, do we have any more questions?
Very impressed. So there were a bunch of questions. I was afraid to interrupt because I didn't want to break the flow of information here, but we actually have a bunch. I don't think we're gonna have time to hit everything. So we only have a few minutes. So if we'll try to get through a couple right now really quick. I also wanted to give Simon a chance to kind of tell the crowd like what's kind of coming next, what's planned. And I'm afraid to say this word, but I will say because it came up a couple times. But hair, what can you share on hair?
I think Michelle and Kira covered a lot of that pretty well. So, bald characters can only go so far. We know that. And so, I think the new hair solvers that the team is working on is coming. We'll announce more details as we have a more firm date when that is. But internally, I mean, we've been looking at this stuff and it's looking great. And we are getting very good performance at the moment. But, there's more work. And I think with whether it's cloth, soft body, or hair, the solver, which is like the engine at the heart of the whole thing, but the tool set also is really important, and that takes time to evolve. So I think what we have out there is a really great set of tools and solvers that people can use today. But we are also going to evolve and add those tools and make it easier as we go forward. So, but in terms of hair, we want to support, we want to get close to real-time hair first, I think, so you can have one or a few characters all run in the same scene and making that easy.
Very cool. Well, thank you for that explanation. We have a lot to look forward to. I'm going to ask this other question from Matt Schwartz from the New Jersey Institute of Technology, only because when I told him we might not get to it, he replied with a very depressing crying emoji. So we'll see if we can help him with this one. How can we step through the animation instead of just playing so we can see the deformable hitting the ground in slow motion? Manual.
I already replied to that.
Oh, you did? Okay.
Oh, okay.
Yeah.
Cool.
Physics debug window has a stepper.
Okay. So
I put a screenshot in that. Yeah.
Perfect. Oh, I see. Okay. So Matt, no need to cry. Okay. He's already give the horns. Okay, cool. Faster than me. All right, great. Well, I can't thank you all enough for spending the time with us today. Is there any kind of last minute tidbit of information that you thought we missed that would be important to shout out loud the last seconds here? Okay, so what we could do, if anybody has time, as typical, I will head over to the community voice chat channel in our Discord. Looks like Wendy will be there. Maybe we'll have a Deformable. Thank you so much. She posted that she's identified the issue with the Twitch resolution, so that'll be fixed next time. Yes, thank you very much, everybody. This is great, jam-packed. I think we need to schedule the next one for, let's say, 6 hours. How does that sound?
6 hours. Got it.
6-hour live stream. All right, thanks, everybody.
Thank you for joining us.
You.
Thank you, everyone.
Bye.
Thanks.
Bye.
Hi, guys.
Bye.
I'm kinda like complicated.
Okay, cool. All right, looks like a couple of them are heading into the voice chats. We'll go there.
That
was great, Wendy. Thank you.
Save me.
Yep, I'll join you in just a minute.
But you appear like a lightning bolt.